This video will explain our latest research on data augmentation and how we can use it to help us understand generalization in artificial intelligence systems based on deep learning. Our paper is titled Investigating the Generalization of Image Classifiers with Augmented Test Sets. Here's a quick overview of the presentation of this paper. We'll start off by describing the use of prior knowledge or inductive biases in artificial intelligence systems based on deep learning, how we can use priors to help to dramatically reduce the search space in finding a solution for these neural networks, searching through some problem space. Then more concretely, we'll take this into the context of computer vision and describe global and local priors for these two-dimensional image pixel grids that are typically used in computer vision deep learning tasks like image classification, bounding box detection, semantic segmentation, or image generation, where we usually have these two-dimensional height-width spatial grids, and we have local priors that may focus on, say, 3x3 windows, as in the convolutional filter, or global priors like the attention layer that focus on the entire height-by-width pixel grid all at once. So then we'll go more into inductive bias in neural networks, the convolutional network versus the attention-based transformer networks, inductive biases in data augmentation, things like cropping, rotation, translation, horizontal flipping, all these different priors that we're injecting into computer vision systems through the data augmentation interface. So we'll use the data augmentation interface to see if we can find a corresponding connection between neural network architectures that are biased towards local solutions like the convolutional network or global solutions like the transformer attention network, and see if the data augmentations that also look for, say, local priors in the cropping, where you say crop out just the dog's nose to classify it as a dog versus a cat, compared to a global augmentation where, say, you add rain to an image and you augment the entire height by width spatial structure, such as, say, a pixel in the top left corner of the 0,0 coordinate is also augmented with this, say, bottom right corner of the 256 by 256 and a 256 by 256 height width image. So we'll look for a connection between architecture and augmentation, describe the experiments that we set up, the results of these experiments, and then what we take away from the experiments. We'll discuss the future work of how we intend to further study the use of data augmentation in understanding generalization, particularly through this lens of computer vision, but also looking to extend this research into natural language processing and some concrete ideas we have for doing this. And then finally, we'll end with opportunities for collaboration if you're interested in doing this work on data augmentation and using the data augmentation interface to study generalization. We'll quickly present the use of prior knowledge in artificial intelligence, although we'd rather transition into the concrete examples of how it's used in computer vision. So from a high level, we might imagine artificial intelligence as being tabula rasa, learning from a blank slate, where we just have a complete blank slate in our learning algorithm and we have no biases as it learns from data. But this isn't really how intelligence is manifested in animals or current AI systems. We usually inject biases, prior knowledge into the systems that help find a reasonable solution and dramatically narrows the search space. So by adding these priors into the system, it gives it a lot more learning signal. This prior knowledge could be in the form of the neural network architecture, the training data itself, the data augmentation, multitask learning losses or regularization penalties, all sorts of ways of injecting these priors into what the solution should look like for the learning system. To provide a more technical analysis of prior knowledge in computer vision, we'll describe how global and local priors are manifested in these two-dimensional image pixel grids. So images are typically represented as pixel grids in tasks like image classification, bounding box detection, and these common tasks in deep learning for computer vision examples. So this is a high-level overview of pixel art, communicating this idea that any image, digital image, can be fine-grained and cut up like this, where you have these 0 to 255 values, 0 being white, 255 being black, and these intermediate values where, say, this would be a black circle with some gray outline on it and then a white background. This can be done at 256 by 256 or 4K high resolution images. This is how images are represented in computer vision. So we might say a global prior would be to look at this entire pixel grid all at once and try to find a signal in it, whereas a local prior would be to just look at this 3x3 window and see if a signal can be found in this local window. We'll begin by describing the prior knowledge manifested in neural network architecture design for computer vision. We'll start off with the convolutional neural network. The convolutional neural network shares weights in a 3x3 or n×n kernel, but typically 3x3, as it slides across an input image pixel grid and then later on intermediate feature maps throughout the sequential processing of a convolutional neural network. It has this local window that it slides across the image, as shown in this diagram, to process the image. So this is a local prior saying that you should look at local neighborhoods of pixels to aggregate information and make a decision about the image. An alternative form of prior knowledge in neural network architecture design is the attention layer. Attention was originally developed for natural language processing applications, and particularly neural machine translation, where you need to attend over a long context in order to make a decision about how to translate a sentence from, say, English to German or French to German and so on. So the attention layer was designed to have this massive attention over a very long context window compared to the convolutional network and the convolutional layer, which is designed to have a small context window and have this kind of pixel local structure with the 3x3 grid compared to the global attention network. This animation from the Google AI blog illustrates the vision transformer, showing how the attention layer has been adapted for computer vision in the vision transformer architecture. This is a very exciting new neural network design for computer vision that we're very excited at looking at different properties of it, such as in this study how it responds to data augmentation. What we're doing is we split the image up into patches and then we apply the global attention over all the patches. So we have sort of a local prior in this, and then we have the global attention. So there's a little bit of a confounding factor with our experiments and trying to single out local and global priors in neural network architecture due to the way these patches are constructed, but we still have a global attention layer in the transformer layers of the vision transformer architecture. As a quick recap, we're referring to the convolutional layers as a local inductive bias or a local prior in computer vision, and the attention layers of the vision transformer model as global priors. Now we'll describe how inductive bias or prior knowledge is used in the data augmentation interface for training deep neural networks. Data augmentations define symmetries in the data. This is also referred to as geometric deep learning, as we look for different ways to use prior knowledge and interfaces to encode symmetries about the data that we're learning from. In the case of images, we say that this is a hamster image even when it's been rotated, the color channels have been manipulated, or it's been flipped upside down, or the edges of the image have been sharpened. These are all examples of symmetries that are encoded in data augmentation, and the prior knowledge biases the neural network to be invariant to each of these different transformations. In our experiments, we're interested in seeing if the global and local spatial priors between the neural network architectures and the data augmentation correspond with each other and interact with each other in a predictable way. So a global prior in augmentation is defined as something that preserves the global structure of the image. We have this original truck image that's been flipped. In this case, the color channels have been manipulated, and we have some cutout in the image in the input space, and we have a similar color transformation with this image on the far right, compared to local priors, which we define as cropping. So when you crop an image, shown here as we only take the windshield of the original truck, we are biasing the model to focus on local regions of the original pixel grid for making the classification that this is a truck rather than an airplane, cat, dog in CIFAR 10 classification. The motivation of our experiments are to find a connection between the inductive priors in neural network architecture and data augmentation. We defined how they both use global and local biases to guide the solutions in computer vision tasks such as image classification. So here are some motivating questions. Does a local prior architecture such as a convolutional neural network perform better than a global prior architecture like the vision transformer on a local augmentation test, so on the crop augmentation test? And we use cropping for our local augmentation test, and we use Gaussian noise as our global augmentation test. And we also use a rotation augmentation test to sanity check the use of global local terminology in our experiments. With that introduction, we'll get into the experiments that we performed for this paper. We start off with an overview of our experimental framework, then identify some potential confounders and linking between the bias in architecture and augmentation, the impact of data augmentation generally as a regularization, preventing of overfitting, and the learning curve of the vision transformer compared to the ResNet convolutional network architecture. Then we'll show the degradation of models trained without data augmentation. This has huge implications for the lack of robustness in these deep computer vision models, more generally outside of our particular linking between the priors and augmentation and architecture. Then we'll describe training with the test augmentation, how using cropping during training helps with the test performance. In our case, it doesn't help. And then we'll look further at the RAND augment scheme. RAND augment is the state-of-the-art strategy for using data augmentation with the training of computer vision models. So here's the high-level overview. We test the convolutional network and the vision transformer, and we test them on the crop test, rotation test, and Gaussian noise test. This is where we take the same testing data used in CIFAR 10, but transform each image with this data augmentation and see how much that changes the performance from the original test set to the augmented test set. We see how using the augmentations during training changes the performance on the test set. So if we train with rotation, does that help with the rotation test set? and so on, with using the baselines of no data augmentation and the very popular state-of-the-art RAND augment strategy for controlling several different augmentations, which we'll explain further. We utilize the RAND augment state-of-the-art augmentation training strategy as a strong baseline for comparing these models and how well they perform on these augmented test sets. The RAND augment training strategy has two hyperparameters. N determines how many data augmentations to apply in sequence. This is selected from a large pool such as rotation, translation, solarize, increasing the brightness, horizontal flipping, and many other different augmentations that are included in the random sampling, with N determining how many to sample from, and M determines the magnitude of the augmentation. So for example, if you're rotating an image, if you have a high magnitude, you rotate it, say, 60 degrees compared to 10 degrees. So also we've identified two potential confounding factors with these experiments. The first of which is the impact of data augmentation during training. So as we study these models without augmentation to try to see if the inductive bias in the convolution and the attention layer corresponds with the test set, we do see that using data augmentation also has a strong regularization effect in preventing overfitting. Particularly in the ResNet, we see a quick overfitting to 98.9% training accuracy, but then only 79.3% testing accuracy, similarly with the vision transformer. And then we find another interesting property of training our vision transformers where they aren't as quick to overfit the training accuracy when trained with RAND augment. We see it takes much longer to train these vision transformers to higher training accuracy, and we see it continuing to improve, although it does saturate around 400 to 500 epochs. And this is challenging because we want to test the ResNet and the vision transformer with a similar amount of computation. So we have this confounder of the computation that's used to train each model, and then also the vision transformer reacting differently to data augmentation. The following experiments will illustrate the performance degradation between the ResNet and the vision transformer when they're trained without any data augmentation and evaluated on test sets that have been transformed with data augmentations. The 50% cropping test crops the images as follows. We have in some cases an extreme cropping where we say only take this one edge of the frog image. In other cases the cropping is more innocuous, such as this overall preservation of the structure of the boat. Gaussian noise, again, we're describing this as a global augmentation where we just add noise and preserve the overall structure of the height width pixel grid. And then as a kind of sanity test intermediate augmentation, which we neither classify as solely local or solely global, we have the rotation augmentation where we rotate the images. Our results do not find a significant link between the local and global priors and architectures and the augmentation. Starting with cropping, we see the vision transformer degrades similarly to the ResNet. We would have expected the ResNet to be better at these small crops because it's being trained with these 3x3 windows that we would think would be robust to these very heavily cropped regions, such as just this edge on the original frog image. However, we don't find this with our experiments. This is another visualization of the vision transformer without any augmentation, degrading as we increase the magnitude of the cropping smaller and smaller patches of the image, and then how the RAND augment strategy does improve performance, but it still degrades as we increase the magnitude of the cropping, similarly with the ResNet. Then using the Gaussian noise test. So first is a quick visualization of what we mean by increasing the strength of Gaussian noise. We start off with this low intensity added pixels, and then we increase it so we're really transforming the image and potentially corrupting the label altogether. So we also don't find any kind of significant difference. We actually find a very surprising that the increased Gaussian noise, which we visualize here to illustrate that we've set up the experiment correctly, still doesn't result in any different performance as we see with the increased levels. To sanity test our evaluation, we also perform the rotation degradation. We see as we increase the magnitude of rotating the images, the performance degrades heavily. In the case of a 50-degree rotation, the performance of the vision transformer drops from 74.4% accuracy to 46.7%. Similarly, the ResNet drops from 79.4% all the way to 43.6% with a 50-degree augmentation. This has huge implications for the lack of robustness in these computer vision models. And similarly, here's another visualization of the degradation as we increase the magnitude. We then look to how training with the augmentation used in testing will impact the performance and see if we can find a link between training with a local prior and then injecting that with a global or local architecture. In this case, we actually do see some performance gain on the global architecture with the local augmentation on the local test set. We see the vision transformer degrades less quickly than the ResNet does on these crop percentages. So we further explore the vision transformer and the different kinds of augmentation strategies we can train it with. So when we use the RAND augment training strategy, we achieve better performance on the original test set because RAND augment is a better augmentation training strategy than only using cropping in augmentation. It's very rare to only use one data augmentation in the training of these models. But we do see that the cropping still holds its own in degradation on pace with the rand augment model. At 75%, the rand augment model is degraded to 75.5%, and the 90% cropping model hangs in there at 72.2%, even though it starts off from a lower point. So we see that maybe there is some correlation between the training and testing, although we don't find an exact match. On the 90% cropping distribution, we don't find the model that's been trained on 90% crops to outperform the model that's been trained with all sorts of different data augmentations. Our experiments further confirm the findings in robustness research and deep learning, particularly finding that deep computer vision models alarmingly lack robustness. We see a huge performance degradation as we crop the test set or we rotate it or add Gaussian noise. This is very alarming for applications such as medical image analysis or self-driving cars, where we'd imagine, say we have different lighting conditions in one hospital compared to another, or we have some slight noise in the imaging. Anything like this could cause a huge degradation in the performance of these models to perform tasks such as COVID detection from chest x-rays, such as a problem that we're studying in our lab. So here are some ideas from future work and how we contextualize these experiments. We see this as being in the avenue of corruption testing, things like ImageNet-C and stylized ImageNet, seeing how these computer vision models, how their performance changes when we introduce these corruptions to the original test data set. Then we're further looking at training strategies with augmented data. We're just looking at taking these X prime examples derived from the original XY pairs and just training with them as in they're any other data, whereas we might look at things like consistency losses, enforcing consistent representations between X and X prime, and other kinds of strategies to use augmented data. We're further looking at using data augmentation for generalization tests. Rather than using IID test sets, we can particularly control the distribution of the test set to understand how these models will react to things like distribution shift. We also have emerging interfaces for data augmentation. Particularly the DALL-E text-to-image model allows us to generate images from natural language prompts. This could allow us to test all sorts of different kinds of generalization cases, such as, say, repeating objects. So rather than just classifying a single horse in the image, we always have 2 horses, 3 horses, or we can remove backgrounds more easily, all sorts of interfaces that we can do with these advances in image generation. And then finally, we have the WILDS dataset benchmark of real-world examples of distribution shift, which we're looking to connect to the prior knowledge in architecture, data augmentation, and the overall framework for how we look at distribution shift and study it with data augmentation. This concludes our presentation of investigating the generalization of image classifiers with augmented test sets. If you're interested in collaborating with us on this research, please email me at cshorten2015@fau.edu. You can also find me on Twitter at cshorten30 or LinkedIn at Connor Shorten. The code for this paper is completely accessible at github.com/cshorten/augmentation lab. This framework includes many other things such as consistency training with augmented data and this overall framework of using train test augmentations to evaluate the generalization of these models. Thank you so much for your time and for listening to this presentation.